Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this video we are going to discuss how to analyze games using game theory. We will do this in the context of two examples of two famous games, The Prisoner's Dilemma and The Battle of the Sexes. Let's start out with The Prisoner's Dilemma. This is probably the most famous game in all of game theory. Since it appears in pop culture, you may have seen some version of this before and not known what it was. In the story of The Prisoner's Dilemma, we have two criminals who have been partners in crime. They are caught and put in separate cells. That gives us our players. We have prisoner number 1 and prisoner number 2. Each is separately offered to make a choice, either incriminate their accomplice, which we call think, or refuse to talk, which we will call silent. These are our strategies. Think or silent for both players. As for the payoffs, if both stay silent, there is not enough evidence and they receive only a short sentence for some minor crime that they have committed. If only one thinks, then he is released and the other serves a long sentence. And finally, if both think, they are both held for a medium sentence. To illustrate the payoffs, we are going to use what we call the normal form game matrix. The game matrix summarizes all the information we have about the game, and it's there that we will specify the specific payoffs. I'm going to draw a 2x2 grid. From there, we have player 1 on the rows and player 2 on the columns. It's arbitrary which one you put where, but I'm always going to do player 1 on the rows, player 2 on the columns. We label each row and column with the potential strategies. Player 1 can either think or stay silent. Player 2 can either think or stay silent. When I write the payoffs in the game matrix, I always write player 1's payoff in the bottom left and player 2's payoff in the upper right. This helps me keep it straight as to whose payoff is whose. Remember that if both players stay silent, then they are charged with a minor crime and receive a short sentence, which we will say is worth 2 utility. If they both think, then they are going to both be held for a medium sentence. We'll give them 1 utility for that, since it's a little bit worse than the short sentence they would get. If player 1 thinks and player 2 stays silent, player 1 gets to go free and get the highest utility possible. We'll call that 3. Player 2, on the other hand, stayed silent, and they're going to get the long sentence, and that's the worst outcome, so we'll give them 0 utility. On the other hand, if player 2 thinks and player 1 stays silent, player 2 goes free and gets 3 utility. Player 1 gets the long sentence and gets 0 utility. Note these are numbers I just made up for this game, but remember what matters with utility is the order of preference. Going free has a utility of 3, so it's the best because it's higher than 2, 1, or 0, and so on down. The other famous game we are going to analyze is called The Battle of the Sexes. In Battle of the Sexes, we have 2 players again, a husband and a wife, which we'll just call player 1 and player 2 again. The husband and wife are planning to meet for some activity in the evening, but for some reason they didn't decide beforehand and can't communicate with each other. Instead, they have to independently choose where to go. There are 2 possible options which constitute our strategies: opera or boxing. We will again use the normal form game matrix to describe the payoffs. Both spouses prefer to be together. If one ends up at opera and the other ends up at boxing, both will be unhappy. They always prefer to be together. But one spouse prefers opera over boxing and the other spouse prefers boxing over opera. We will again use the normal form game matrix to describe this. Since we have 2 players and 2 strategies, I'm again going to make a 2x2 grid. In situations where we have more than 3 options, then the grid will be a bit bigger. I'm again going to put player 1 on the rows and player 2 on the columns. The 2 options are opera and boxing for both players. In both of the games that we've talked about here, the 2 players have the same choices, but that does not necessarily need to be the case. If player 1 goes to boxing and player 2 goes to opera, they are not together and they're both unhappy and get 0 utility each. Same thing if player 1 goes to opera and player 2 goes to boxing. If both players end up at opera, then they're happier than if they were alone, but player 1 really enjoys opera and gets 2 utility. Player 2 is not as big of a fan of opera and gets 1 utility. If both end up at boxing, player 1 is okay with it and gets a 1, and player 2 really enjoys boxing and gets a 2. Now that we've delineated our 2 example games, let's talk about how to analyze them. The first thing we need to do is find the best responses. The best response is a strategy that a player can follow that maximizes their utility given what the other player is doing. I'm going to write this out formally and then discuss what it means. Strategy SI is a best response if player I's utility that they get from SI and S not I, remember that S not I is the other player's strategy, is at least as high as the utility that they get from SI prime and S not I for all SI prime in the strategy set big SI. This mathematical statement might look a little intimidating and confusing at first, but actually it's pretty simple if we break it down. This tells us that strategy SI is a best response if it's impossible to improve the player's utility by switching to any other strategy. S not I, the other player's strategy, remains constant. We are fixing the other player's strategy and picking the best response to that strategy. Note that it's possible for there to be multiple strategies to be a best response if there is a tie. Remember that a best response has to condition on the other player's strategies. In the games that we've talked about, each player has 2 possible actions. This means that to define player 1's best response, we need to specify 2 different actions depending on what we think player 2 is going to do. The same thing goes for player 2, who must condition their best response on an action by player 1. Let's go back to the prisoner's dilemma and talk about the best responses. To discuss player 1's best response, we need to specify what player 2 is going to do. First, let's assume that player 2 finks. I'm going to cover up the half of the game where player 2 stays silent, and we're just going to look at what player 1's best response is going to be. If player 1 also finks, they get 1 utility, but if they stay silent, they get 0. Therefore, it's better for player 1 to fink. I'm going to underline player 1's best responses with red, and I'll write down that player 1 is going to fink. Now let's think about what player 1 should do if player 2 stays silent. Now I'm going to cover up the half of the chart where player 2 finks, and we'll look just at when they stay silent. Player 1 is now deciding whether to fink or stay silent and choosing between getting 3 utility or 2 utility. They of course prefer 3 utility, so I'm going to underline that and write down that they fink. We've now fully defined player 1's best response function. We can see what their best response is for all the possible actions from player 2. In this case, the best response is always just to fink, no matter what the other player does. When one action is always the best choice, we call it a dominant strategy. But that's definitely not always a thing that happens. Now let's look at player 2's best response. I'm going to underline player 2's best responses in blue. First, consider if player 1 finks. We'll cover up the half of the chart where player 1 stays silent, and we'll look just at player 2's payoffs. 1 is better than 0, so they're going to prefer to fink. Next, if player 1 stays silent, what should player 2 do? We'll cover up the half of the chart where player 1 finks, and look at player 2's payoffs. 3 is better than 2, so they are going to, again, prefer to fink. Since this game was completely symmetric, it's no surprise that the 2 best responses look exactly like each other. Going back over to Battle of the Sexes, let's look at the best responses here. For player 1, we're going to look at, again, 2 possibilities. If player 2 goes to opera, and if player 2 goes to boxing. If player 2 goes to opera, we'll cover up the half of the chart where they had gone to boxing and compare the payoffs for player 1. Player 1 would rather have 2 utility than 0 utility, so they are going to also go to opera. If we look at the half of the chart where player 2 goes to boxing, player 1's now picking between 0 and 1. They'd prefer to have 1, so they're also going to go to boxing. So I'll fill these in. Now for player 2, the best response function must again consider all possibilities. So if player 1 goes to opera or player 1 goes to boxing, what should we do? If we look at just what happens if player 1 goes to opera, player 2 prefers to get 1 utility instead of 0 utility, so they prefer to go to opera. Now if we look at just the half of the chart where player 1 goes to boxing, player 2 prefers to go to boxing because 2 is better than 0. Now that we know how to find the best response functions, we are ready to discuss the Nash Equilibrium. Our main goal in solving games is to find the Nash Equilibria. There could be one or there could be multiple. Formally, we are going to define the Nash Equilibrium as a set of strategies, S1 star, S2 star, and so forth, all the way up to Sn star. So we have a strategy specified for every single player in the game, such that for player I, Si star, and remember Si could be any of our strategies here, S1 star, S2 star, and so on, is a best response to all the other players' strategies S not I star. If every player is best responding to one another, no player would be better off by changing their strategy. Again, this assumes that all the other players will still follow their Nash Equilibrium strategies. An intuitive way to think about Nash Equilibrium is that there are no regrets. Once the game is over and every player has seen what every other player picked, each player would be satisfied in saying that they couldn't have done better by picking something else. In the simple games that we've represented with normal form game matrices, the easiest way to find the Nash Equilibrium is to find the boxes in the matrix where we've underlined best responses for both players. In the prisoner's dilemma, we can see that there is one box where both players are best responding, and that is this one right here where both players think. So we'll describe the Nash Equilibrium as an ordered pair for the strategies think, think. To describe the Nash Equilibrium, we need to describe the actions that are being taken, not the payoffs. So the Nash Equilibrium here is not 1 and 1, it is think and think. 1 and 1 are the payoffs that they get in the Nash Equilibrium. Note that the Nash Equilibrium is not necessarily the best outcome for the players. Had they played cooperatively and both stayed silent, they would have ended up in the bottom right and both done better than they end up doing in the Nash Equilibrium. However, silent and silent is not a Nash Equilibrium because players can improve their payoff by switching. Player 1 has a payoff of 2, but could improve to a payoff of 3 by switching to think. Player 2 also has a payoff of 2 in silent silent, but can also improve their payoff by switching to silent. So this cannot be a Nash Equilibrium because players can do better by switching. These off-diagonal boxes are also not Nash Equilibria because players can improve by switching as well. In the upper right box, player 2 can improve by switching to think, and in the bottom left box, player 1 can improve from 0 to 1 by switching from silent to think. We can see that the only possibility for the Nash Equilibrium is think and think. So what we get is players pursuing their own self-interest leads to a point where everybody's worse off. This is a concept we will return to later on when we discuss oligopolies. Returning to the Battle of the Sexes, we can see there are two Nash Equilibria, opera and opera, and boxing and boxing. We can see that in this game, the two equilibria that we get are always where the two players choose the same action. For this reason, this type of game is called a coordination game. Unlike in the prisoner's dilemma, the battle of the sexes does not have a dominant strategy. The best choice always depends on what the other person is doing. We can also clearly see here that if we are in either of these Nash equilibria, no one can improve their strategy by switching, because if they switch, they would end up alone and getting 0 utility. The off-diagonal boxes, where they are alone, cannot be Nash equilibria because both players could improve the outcome by switching to where the other person is. I do want to point out here that we are just talking about what we call pure strategy Nash equilibria in this course. There is a second type of Nash equilibrium called a mixed strategy Nash equilibrium, where the players randomize between choices, and there is in fact one of those equilibria in the Battle of the Sexes, but we are not going to get into that in this course. In our next and final video, we are going to discuss some applications of game theory into economics.